Yeah, as Jimmy said, about a year ago, I started work for Jimmy, and he asked me to have a look on language tooling for domain-specific language he was designing. I knew nothing about language-oriented programming at that time, so I started to Google, as you do, starting to read about compilers and parsing, lexing and scanning, and realized that there's a ton of technical complexities in this, which is super fun, of course. But does the end user really care about your compiler? Probably not. And since for domain-specific languages we are targeting both programmers as well as non-programmers, and a non-programmer definitely do not care about your compiler. They most likely care more about an editor or the editing experience, being able to express themselves and have that support and guidance that they need. So Jimmy didn't specify a compiler, he said language tooling. And so I started to read up on how you do editor support as well, since that is equally important. This talk will be about this year, what I've learned so far, having built a few of these tools, and what I think you should focus on, and a few things which I think are more important. This will be slightly technical. I know that not all here are programmers, but in order to get to the editor, because this is where we want to be close to the user. Imagine a user here. We need to navigate through a few technical areas. For those who have studied computer science, you might have remembered this is our basically compiler subjects, techniques. And since these can be distractions, they are quite fun. It's easy to get stuck here, but this is the target. This is where we want to be. This is where we can add value in a domain-specific language. In order to do that and to do it good, or you need to have, there's a few data structures which are more important than others in terms of editor support. So that's why we need to talk about that, because that lays the foundation for the editor. So if you're a non-technical person, please hang in there. If it gets complicated, it will be less complicated at the end. So general purpose languages, this is how they depict it. There's a book called The Dragon Book about compilers, with a knight in shiny armor. It's supposed to be hard, it's complex, only for the brave people. And it is. Only parsing is quite complex, but there's a lot done in that field in computer science on how you parse and complexities in parsing and things like that. You have type theory. I know at least one person in this audience who's very good at this in Haskell, and you have Scala, and type theory is hard. So it is hard with general purpose languages. And then you have bytecode, machine code you need to generate, maybe on multiple platforms. Also very hard, very complex. And then you have libraries and ecosystems you need to support, so you cannot break compatibility in a general purpose language. Should have mentioned maybe that general purpose language is like a language which is used for general purpose, you can build like any program in these languages. It's like C#, Java, something like that. And they are hard, but I think that sometimes I, as a person, have a picture that it's super hard and I need to know all this stuff. And I still think the community sometimes give that feeling as well. So the other week I was reading through some Hacker News comments. It's part of my evening routine before I fall asleep. I always read Hacker News comments. Then my day turned out to be pretty good after all. It's a toxic environment. And there was this person who laid out some details about the programming language he or she wanted to build, and it was immediately killed in the comments. You don't know enough about type theory, you don't know enough about functional programming, you don't know about parsing. And that's like, first of all, it's not constructive, it's pretty toxic. That doesn't help anyone in any situation. But that's according to me, that's the feeling someone wants to project, and that's the feeling I can have looking from the outside, that I need to know all these things. Luckily, domain-specific languages doesn't need to be that complicated. First of all, they are specific. They are not generic. They are not. You don't have a domain-specific language designed to solve every problem. They are specific. It's in the name. They can be simpler, and simple is a vague term, but they are more. Martin said they are more concise in their grammar. They may be on a higher level, so they are simpler. They are not as complex. You don't have to generate bytecode or machine code. Many DSLs transpiles or transform into something else, maybe something on the same level of abstraction, just another format. So that's a lot easier than to do bytecode or machine code. You have a much smaller ecosystem. The users of your language and the chances of having libraries and things like that is often within your control as a company, or at least easier to control than a general purpose language. So you can be agile. Also, as Martin said, you need to be agile and flexible, change things. That's also a lot easier in a domain-specific language. Maybe you even have control of all the existing source code in your language, and after change, you can have a tool that changes it for you, or you can transform it in some way. So that's an advantage you can have. There's, however, one thing you cannot escape from, even in domain-specific language, and that's some sort of compiler. It's in quotes because it can be a transpiler. Some people call it a generator, a transformer. But let's go with compiler. It sounds cooler, sounds more advanced. But you have a piece of source which is in text, which you need to parse so you can understand what the text says. And you need to analyze that program to find errors, or to find improvements you want to hint to the user. And then finally, you need to transform that to something which is unique in your situation. Maybe it's a dedicated runtime, and then it might be an interpreted language if you just consume the parsed language, or you transform it to an output of some kind. Strictly speaking, I've only built transpilers, so that they are roughly on the same abstraction level. But I think that many people hear transpiler and they think JavaScript languages. That's not the case here. So we'll start with the details on parsing, analyzing, and transforming a source. We have this is our example language. This is a DSL we use at work in a few projects. It's a DSL tailored for domain-driven design, so I guess that makes it a DDD DSL. Luckily, that's not the file extension. It's very model-centric and to be declarative. So we define a value or an entity of type value at the top, which has two properties. We have a process for signing up attendees, where you can send in an attendee and then we have some expression. What this program does, it's not that important for the presentation, but this is what we're going to use as example throughout the talk. One thing about our language splat is that we have a subset of the language is JSON, so you can use JSON to meta describe a few things, and we're going to look on how we parse JSON as an example. I took that because it might be easier to get through in examples. They are pretty small, and I guess that most of you are familiar with JSON. Yeah. When we transpile the splat code, we have a specific, very tailored runtime that consumes the output, the transformed output. So it's a compiled language, but with a runtime that then reads the output and produces types and with these characteristics. So let's start with parsing. This is the JSON structure. So we have a super simple object. When we read it, for the computer, it's just a sequence of characters. There's no structure to it, it's just characters. But to us, they have meaning. So first we have a left curly. Then we have a new line, 2 spaces, which are they are not significant, so we don't care about them. Then we have something that starts with quotes and ends with quotes, and that's a string. We have a colon, which is the limiter between an attribute's name and the attribute's value. And the number is 2 digits, but it's a number with 2 characters. Another insignificant character, which is new line, and then we end it all with the right curly. These are called tokens, and what you need to do in a compiler is that you need to identify these tokens in your stream of characters, or in your source code, basically. This is also known as lexing and tokenizing, but what you want is you want to identify these tokens. These have meaning in your language, and then you want to build a grammar using these tokens. Here is one of the traps. It's easy to get stuck here and do a lot of coding, and it's fun, but it's not really helping you in the end. So I don't think you should handwrite your parsers and your lexers. I think you can be more meta than that, so you can use a parser generator. And what a parser generator is that you have, it's a dedicated tool which you feed with a formal definition of your grammar, and it will output a parser that understands that grammar. And then you use that output in your compiler to read your source code, compile it to a structure. That's why it's meta, because you use a DSL in a compiler to generate the parser, which you use in your compiler. But it's all about having a tool generate the parser for you, so that you don't have to do the lexing and parsing yourself. This tool is in a language, so I've used a tool called Antler, which we'll get to soon. It's in Java, but it will produce a code in another target or a host language. So in my case, I've implemented the compiler in TypeScript. So you just use a tool to bootstrap you so that you get a parser based on grammar. And we're going to look at how that grammar can look like. But the benefit is that you can regenerate your parser, you can change your grammar, generate a new one pretty easily. So Antler, I can't remember the acronym. It's been around for quite a while. It's a Java-based tool. It's a Java-based parser generator. It's grammar-driven, so they have a specific grammar, which we'll look at for defining your DSL. You can produce parsers in multiple languages like Java, C#, JavaScript. I chose Antler because there's books about it. There's active community on Stack Overflow. There's articles written about it, so it's pretty easy to find help and assistance when you need it. This is not the only tool available, and there are other tools for various languages you can use. I recommend Antler. I think it's been good. So what you feed Antler is a definition of your lexer rules. So the previous slide where we identified the characters in the JSON structure, you give Antler a formal definition of that, or patterns. It's like the left curly and the right curly are objects start and end. And then it gets more complicated. Here we have rules, which resembles, it's a pattern, so it's, if you know regular expressions, might be familiar. So a number can start with a minus sign. It's optional due to the question mark. It's followed by an integer, and then we have a group with a period and possibly more integers. So that's how you specify the rules for tokenizing your language. That is to identify the words which have meaning in your language. So you do this, and then you have also have the grammar, which is based on these lexical tokens, and it looks like this. So here we have the grammar for JSON. It's a subset of JSON, because let's start with a JSON object on line number 5. So the smallest piece of a valid JSON object would be 2 curly braces, one for opening and one for closing. That's on line 7. Or a JSON object can be a start token, which is still the curly then, followed by an attribute, and then in the next group, with comma separated, more attributes. And then we look on the attribute rule. Here we see that it's a string with a colon followed by a value. A value can be a string, it can be true or false in number. And that's how you build your grammar. So it's similar to a notation called BNF, or I think it's ABNF, Bacchus Now form, which is really similar in parser generators and in parsing in general. So you use that to express your grammar, and you feed it to Antler, the tool, and it will produce a parser for you. It's that simple. Now, when you get familiar with that, it's pretty simple, and if you're going to be agile while developing your DSL, it's a great benefit of not having to change your parser. If you do significant changes to your grammar or want to experiment with things, you can just generate a new parser. That's pretty fast, definitely faster than handwriting it. So now that we have a parser, so we can interpret our source code into tokens, Antler will give us a syntax tree. A syntax tree is a tree structure, data structure, with the grammar and the tokens in a single tree. And let's look on how a tree can look like. So on the left we have another JSON structure, slightly more complicated, but not specifically complicated. And then you have a JSON object, which is determined by the curlers. You have a attribute with value foo, a name foo with a value of 42, and then you have an attribute bar which contains an array which contains 2 Boolean values. So this is known as a syntax tree. The one that Antler will give you is called a concrete syntax tree. It still contains tokens related to parsing, such as the curly braces. The curly braces are good when you read text, but you don't necessarily need them anymore, because you maybe are used to grouping things, and you instead want to use objects for grouping in your tree. So you want something a bit less concrete, something a bit more abstract, and that's what you have, the abstract syntax tree. So you want to get rid of the finer details in text. You want some more abstract representation, but you still want it to be close to text, because remember, the end goal is to have an editor that's about text, so you want it to be fairly close to text anyway. This is a fragment of what a parser generated by Antler will look like. So we'll have functions for grammar rules. So when you enter a rule and when you exit a rule. So if we look on the grammar definition again, you can see that you have JSON objects. Then we have enter JSON object and exit JSON object. And then we have the same for all these grammars. And this is basically a visitor. So while Antler parses your input, you will get calls to your visitor saying, okay, I'm about to parse the JSON attribute now. And then when it's done, it will say, okay, now I've done it. Here's the result. And then you can use that to build your AST, the one we looked at, to populate it with the details you want. So you still need to do some coding in terms of getting from the parser to build your tree structure. And you want to do it, here we derive from the generated listener interface, because you don't want to customize and modify the generated parser that Antler produce, because that will limit your agility. Then if you change that, next time you generate it, you will either overwrite it or you'll have to manually update and patch it. So you want to have them as separated as possible. So AST is one of the foundations, the most important structure when it comes to editor support, and it's also used very much in a compiler. But there's another thing as well, which is called symbols and a symbol table. And again, if we look on this example DSL we have, we can see that we have scopes. Like in the root scope, we have two symbols. We have attendee, which is a value, and then we have sign up, which is a process. The attendee has a name and email, which is in a child scope. So it's an isolated, it's a nested scope. And then we have submit, which has its own scope. And then in submit you have attendee, which is the parameter here. And what you use scopes for is to guarantee uniqueness, for instance, so that you have the identifier for something needs to be unique within its scope, or maybe even within its, like the ancestor branch needs to be unique all the way up. You should use symbols like here something is declared, or at this position it's reference to something. Then you can use that to find errors. So you use it to do something which is called a semantic analysis. And that is basically that you walk through your syntax tree and your symbol table, and you can do things like, are all the identifiers declared in the reference in scope, or do we have duplicate identifiers within a single scope? That's an error. If we have a typed language, you can check that, okay, is this references of the right type to what it's referring to? If it's not, it's an error. And then you analyze your AST, which is the abstract representation of your program, together with all the symbols you have, and you use that to find errors. Use it to check like the function. If I'm calling a function, like, is it protected? Is it private? Things like that. So this semantic analysis is really based on the AST. So you will visit your AST over and over, but you want to do it as few times as possible because you don't want to traverse the tree unnecessarily. It's expensive. So what I've learned is that you should really invest in an AST and a symbol table which is suitable for the analysis you are going to make in your tooling. So invest in making it fast, having the appropriate query methods or searching, so you can easily traverse it. You can find errors and fail fast basically. So provide good and detailed error messages for a user if there's an error in the program. So we have another slide of this AST, and if the same example on the left. So if we look at the root node, it will have a value node, which is the attendee. That will have an identifier node, which is that node. The value node would be that one. And then it has two field nodes. And each field node will also have an identifier, like name and email. The AST is yours. I mean, you build it the way you want. You enrich it with the information that you need. It's common to have references back to the source file, the line, the column, so they can both identify it when we get to the editor. You want to be able to provide errors as detailed as possible. But it's basically a tree structure that resembles your program. The transformation part is that when you have parsed, you have built your tree structure, you have the symbols, you have analyzed it, and everything looks fine, you need to produce an output. How complex that is very hard for me to say. It's very much dependent on what your target is. As I said, I worked on high-level DSLs where we have been transpiling, so it's been one-to-one. So for each source file has been a corresponding output file. Pretty much like Java and classes, but simpler. And then it's fairly easy to transform it. It has been in those cases, but it can be complex depending on what you want to do. And sometimes the AST, the tree, and the symbol table are just not good enough. They're a bit too rough. They're pretty much tied to the syntax of your language. Maybe you want something else. That's called an intermediate representation. That is something which is more semantic to your model, to your domain. So you use the AST or a program to enrich another model, which you then transform. Super simple example I've used. I made a very small text DSL to produce sequence diagrams in SVG. I made a syntax tree and all that, but then I walked that tree and built a sort of view model where I looked up all the actors and all the messages, calculated all the offsets and positions of every element, and then I just templated over that object. That was a sort of intermediate representation which made the templating much easier. Yeah, you can produce one or more outputs. It's basically up to you. The ones I've used has been based on an AST visitor as well. So here again, AST visitors are super important. And that's it. Then you have a compiler. It's maybe sounds a bit too easy, but the transformation step is super hard to say do like this because it's very unique to your problem. But in terms of an editor, now or in terms of a compiler, we now transform some input to output. But how is that compiler invoked? How are your users getting to use it? Most likely command line tool. Don't know if non-programmers or business users want to use that. Will they use it if it's just a compiler? It will sure limit the adoption rate you're aiming for, right? It's just a compiler. You haven't really solved the problem from a business perspective. You have maybe solved it from a technical perspective. So that's when we get to the editor. So the good thing about the compiler is like there's fewer choices there. When it comes to editors, it's like religion. So which editor will you choose? Which platforms do you need support? Is it web? Is it native? There's a lot of things to choose from. And it's pretty expensive to build editor support for all editors in the world or even in your organization. Luckily, a few years ago, Microsoft released an editor called Visual Studio Code. And as part of that, they defined something they call a language server protocol. The language server protocol is basically, before you had everything in the editor running in the same process, maybe different threads, but they wanted to split that for multiple reasons. First, they didn't want the editor to be slow and unresponsive to lock up the UI thread due to a bad plugin. And then they realized that if we have this separated, we can have all the language smartness in a server. We can communicate with the editor, which is basically a view of that, over RPC. And then all of a sudden you can write your language servers in any language and support an editor. Or for C# already, which you can rely on and build support. So it's a separate process. It's meant to be running on the same machine, but it's a separate process. It's JSON RPC over the wire. There are a few editors that support this. It's VS Code, of course, Atom, Emacs, VI. I even think there's something for JetBrains. And Microsoft has also released good client libraries that you can use to build your server if you want to build it in TypeScript at least. But there are libraries for other languages as well provided by the community. So we're going to look at the language server protocol. And we're going to start with, this is Visual Studio Code, by the way, for those who haven't seen it. So it's a pretty standard editor. but it's a little more than an editor. It has some more advanced features than just editing. You have like debugging, version support, but you also have like refactoring. You have go to definition, things like that hidden or available in the editor. I've used it. I think it's a very good editor. So that will be the editor we will look at when looking at the editor feature in the language server protocol. It will still be like circulating around Visual Studio Code. So one of the first features people think about when it's editing support or editor support, it's syntax highlighting. Just being able to see something highlighted reasonably in your DSL. Some people have to have it. Few people want like grayscale. Most people want like a rainbow of colors. But you want to have it themable anyway. So you want the colorization done by the editor, but you want the classification of tokens done by something which understands the program. This is pretty much similar to the lexing we talked about in the beginning. Unfortunately, this is not yet supported by the language server protocol. This is to be done in the editor process. There are discussions going on Microsoft's GitHub to have this in the protocol, because since we did the lexing and all the analysis, we know what each word is. We know it on the server already. We know it when the language, the compiler we built. So we need to repeat a few of those in the editor, unfortunately. So it was a nice effect when I wobbled. So what you want to do is you want to identify like text. It belongs to the Splat. It's a Splat source, but it's a primitive type, and then it gets colorized according to your theme. So you don't specify colors. That's a theme. You just specify this word is a token of this type, and then you leave it to the theme to determine which color it is. And we have sign up here, which is it's not a class, but it's the closest thing. So I categorize as this is a class basically, and then as I said, the colors come from the theme. So you do that for all your important words, the ones you want to highlight. And then you do that by specifying these patterns. These are regular expressions. So what you want to do, or have to do, is that you need to provide a rule. So in this one, we capture like an identifier followed by a white space, followed by any of the words in this list. In value was the one we used, and then the first group is classified as a type class, and the other one is like the storage type class, which is like the built-in class, like the what do you call it? Yeah, the built-in type. And then you have to do that for all of your language. It's not terribly complicated, but I think if it gets included in the language server protocol, I think that would be great. I guess there might be an issue with latency and that you don't want to have a delay in colorization when you open a file. The next feature, which I think is very important in terms of an editor, is diagnostics. So having pretty colors is nice, but having the editor tell me when I've done a mistake or an error is super important. So you want to, the red squiggly line, you want to have it, give it a message, maybe some column marker. You get it here. It's basically everywhere. Like there's an error here, better look into that. And that's also included in the language server protocol. So that can be basically anything. It can be an error, can be a warning, a lint message. It's pushed from the language server. So the language server, once a file is opened, it gets notified and it can do parsing and it can push errors like to the client saying, okay, there's errors on these locations. And the client, the editor, will render that, but it will only render it. So if the file is changed, it's up to the server to send a new list of messages or errors. And these are basically just the result of the syntactical and the semantical analysis. The semantical analysis was when we did the tree walking. The syntax highlighting in our case, is done by the parser. So that's given by Antler. So you just hook in your error handler, and you get notified by Antler when there's a syntax error. So you can combine both syntax and semantics in your errors. Go to definition is another. I guess that these are my top 3 features in editors. Like I want colors, errors, and I want to be able to navigate between like where is this defined or declared. If you control click and hover your mouse, you will get an underline looking like a hyperlink. If you click it, it will navigate to wherever that is declared. In this case, it's in the same file, so the editor will go there. It's the same thing here. The editor will tell the server, so it will be initiated from the client saying, okay, I'm in this file, this is the URI, this is my position, and it expects a reply with 1 or more locations, which are possible definitions of this thing if you have multiple definitions. So what you need to do is you need to have a look in the AST to find this symbol, and in the symbol table to see where is this defined. And then you return that position to the client, and if it's a single position, it will just auto-navigate there when you click it. If you return multiple, it will present a list or some fisheye in VS Code. And that's it. So this is another situation where both the AST and the symbol table are very important. We have another DSL compiler we use at work, which doesn't have an AST, which doesn't have, or very, very limited symbol table, which makes these tools incredibly hard to do, because we don't have that information. We can't reason about the program. It's just being transformed in a single phase in the compiler, which makes it really hard to provide editor support. A few other language server protocol features is code completion. So I'm at this location, what's available to me? What's available in my scope, for instance, or in my type? Code completion is really hard if you have while you type code, or if you have invalid code, because then you need to be able to parse something which is not valid. I haven't reached that point yet. That's quite complicated, I think. It has a feature for renaming. Again, use the AST and use the symbol table, find references, and you can rename like you expect in an editor. I want to rename this and all references to it. You have code actions, which might be pretty print, format this, like go do, or whatever you want to. So you have initiated things from the client to the language server. And there's more. So the specification is open source. It's available on Microsoft GitHub. There's quite a lot of features in it. I've only used a few of them, but there's quite a lot of features that you expect from a modern editor. And I think if you provide a DSL, these features are equally important, or even more important if your target audiences are non-programmers. So wrapping up, I think you should use tools for parsing, at least initially. It's super easy to get stuck, or stuck in an impossible way. It's fun, so you spend a lot of time there. It doesn't necessarily add value. So use tools for it. Focus on the data structures, which is important for the compiler, but are equally important for editor support, in this case the language server. That is the AST and the symbol table. So focus on those. That's the right level of abstraction. You should implement a language server so they can target multiple editors with one implementation. I really recommend Visual Studio Code, at least for doing that development, because you have some built-in debug tools and utilities, so it's much easier. And that's it. That's all you need to know to start writing your own language. No, really, there's a lot of complexities in the details, but if you just ignore them, you'll be fine. That's